So as you maybe have followed in the news or something, the situation with the COVID in Italy is getting worse nowadays, so it's not so good. And so we ask you to be careful and take this into account. In particular, we would very much like you to, as much as possible, not leave the ICTP campus and don't go in town, at least if you don't really need to. And in particular, don't, have parties or something like that, or go with a group there to do something. Just better try to, to stay here as much as possible, because, we are a little bit worried. And so anyway, we ask for your understanding, so for this. Okay, so maybe I will start now. So we're talking about the symmetric group. And so we had shown that every element in the symmetric group has a cycle decomposition, and used this to classify the conjugacy classes of the symmetric group. Now I wanted to briefly talk about the sign of a permutation. And then introduce the alternating group. So I expect you are familiar of the sign of permutation also, for instance, from linear algebra. It comes up when one does a determinant, but I do it in a slightly different way. I make this slightly crazy definition. So for an integer n in Z, and so say for sigma, an element in the symmetric group, the sign of sigma is the following thing. Is defined to be this epsilon of sigma, and I just write down this thing, product over all ij, with I bigger than j, sigma I minus sigma of j divided by I minus j. So this means it's over all pairs of numbers from 1 to n, such that the first one is bigger than the second, and we write this. Now, this looks a little bit crazy because it doesn't even look like it has to be an integer, and I tell you it's supposed to be a sign. But anyway, let's check. And now, now, however, we have the following lemma. First, it is a sign. Epsilon of sigma is minus 1 to the m, where m is the number of all pairs ij in one, obviously from one in the set 1n, with I bigger than j and sigma of I smaller than sigma of j. So it's the number. So the number of pairs, so that the first one is bigger than the second, but the order gets reversed. And the second statement is that this epsilon is a map from the symmetric group to the set 1 and minus 1 with multiplication is a group homomorphism. So the what? What? Where? The sign, yeah. No, the sign of I don't understand. The sign of a permutation. Definition for sigma in Sn, the sign of sigma is this. What? Well, I claim it's not a rational number. I claim it's a sign. It's plus or minus 1. No. No. It's just this. I claim that this is plus or minus 1. Okay? It looks like a rational number, but it's plus or minus 1. And the third one is if sigma is a product of transpositions, where tau I are transpositions, then epsilon of sigma is equal to minus 1 to the k, to the number of transpositions you need. Now, obviously, you are quite right. It is surprising that this should be a sign. But, that's just how it is. So let's prove it. So then we can also see why it's the case. So I want to prove the first part. So I write down the numerator and reformulate it in such a way that it becomes plus minus 1 times the denominator. So if I take the product of all I bigger, so maybe the pairs ij, such that I is bigger than j, sigma I minus sigma j. Now, I can divide this into two halves. Either I is bigger than j and sigma I is bigger than sigma j, or it's smaller. So this is the product over, over all I bigger than j, such that sigma I is bigger than sigma j of this thing times the corresponding product where the order is the other way around. So that's not very surprising. But now, if the order is like this, I can in each time exchange the order. So in each of these factors, let's exchange the order. Each time I get a factor minus 1. And now we have that I is smaller than j, but sigma I is bigger than sigma j after doing this. So what we get is this is equal to minus 1 to the m, which is, as m is this number, as many times as this happens, such the product over all I and j, such that sigma I is bigger than sigma j of sigma I minus sigma j. No? And now, here, whether I sum over all, so sigma is a this is just a reordering of these terms. Now, whether I call these things sigma of I or sigma of j, this is just the same as the sum over all ij, such that I is bigger than over the sum of the product over all ij, I minus j. No? So this is just minus 1 to the m, product over all I bigger than j, I minus j. And so you see, if you take the quotient of these two, you get minus 1 to the m. Okay, so this was the first. The second is that this is supposed to be a group homomorphism. So we have to see that if we take a composition of two elements in the symmetric group, then this goes for the product. So let's see how that goes. So what do we get for the composition? We get the product over all I bigger than j. So sigma of tau of I, so sigma and tau are transpositions, minus sigma of tau, not transpositions, are elements in the symmetric group. divided by I minus j. And we have to express this in terms of the thing for sigma and tau. The first step, we can multiply by 1 in the usual way. So multiply by something and divide by the same thing. So this is the product over all I bigger than j of sigma of tau of I minus sigma of tau of j, a bit too high maybe, divided by tau of I minus tau of j times the product over all I bigger than j of tau of I minus tau of j divided by I minus j. So this is already the thing for tau, but this one looks a bit different from what we want. Now, if we want that this is the product of the corresponding things for sigma and tau, we should here have sigma of tau of I minus sigma of tau of j divided by I minus j. So it's not quite the right thing. So we have to look at this a bit better. So sigma of tau of I minus sigma of tau of j. So if I have a look at this thing, now we can apply basically the same trick as before. So now if I is bigger than j and tau of I is smaller than tau of j, we want to exchange the order. If we do this, we get a sign here, but we also exchange these. We also get a sign here. So altogether, we get the same thing. So we can as well assume, instead of that I is bigger than j, that tau of I is bigger than tau of j. So this is the same as a product over all ij such that tau of I is bigger than tau of j, sigma of tau of I minus sigma of tau of j divided by tau of I minus tau of j. But now we have the same thing as before. These tau of i's and tau of j's run through all possibles. So I can as well call tau of I and tau of j, and then did I want to do that? Now I did a bit too much. Oh, no, that's precisely right. So this is then equal to the product over all I bigger than j, sigma of I minus sigma of j divided by I minus j. And so we find that this thing is equal to the corresponding thing for tau times the corresponding thing for sigma. And so it's a homomorphism. OK. Now, and the third statement is a direct consequence. Namely, if we have a transposition, then this epsilon of sigma will be minus 1. So, namely, so if tau is the proposition ij, then epsilon of tau, by definition, is j. Well, so the only thing where something happens is where it's not 1 divided by 1, it's just j minus I divided by I minus j is equal to minus 1. And obviously, we have all the other factors. Every other k is sent to the same k. So we have, all the other factors are the same. OK, and thus it follows by 2. No, I can write if I write this as a product of transposition for each of them, I get a factor minus 1, and then that's it. OK, so this was this. This was the sign of a permutation. And then, so once we have the sign, we can talk in particular about even permutations. So definition. So permutation sigma in Sn is called even if epsilon of sigma is equal to 1, which is equivalent to saying that if I write it as a product of transpositions, I always need an even number of transpositions. And so the set of even permutations in Sn is called the alternating group maybe small alternating group An. Clearly, as it is by definition the kernel of this homomorphism, epsilon from Sn to this group, 1 minus 1 with multiplication, so it's a normal subgroup. Of Sn as kernel of epsilon from Sn to 1 minus 1 with multiplication, like this. Okay. Okay, so we have the symmetric group always has this normal subgroup. So thus, we have that Sn is not simple for n bigger or equal to 3. So, because, okay, so in S2, obviously the only even permutation is the trivial one. And so a theorem I'm not going to prove, but which I just wanted to mention because it also plays a role later, is that An is usually simple, so is simple for n different from 4. So maybe you can, this is actually not so trivial to prove, but as an exercise, you can check. I mean, the first is clear, A1 and is equal to A2 is just a trivial group. A3 will be the cyclic, the 3 cycles, and this will be isomorphic to Z3. And A4 is not simple. Namely, A4 will contain the following. So the set consisting of the neutral element and this pair of disjoint 2 cycles. And 1, 4, 2, 3. So you have this form a subgroup with 4 elements, and in fact, it's a normal subgroup. Obviously, this consists of even permutations, and so this is the only case, but otherwise, these ANs are always simple. And this fact will actually later show that if you have a general polynomial of degree 5 or bigger in one variable, then its zeros cannot be expressed just in terms of taking nth roots and addition and multiplication. So cannot be expressed in terms of radicals. This follows by some complicated way from this, as we shall see later. Okay, so this was as much as I wanted to say for the moment about the symmetric group. Now we come to the last chapter we have on groups, which are the Pseudo theorems. after, I think, the Danish mathematician Silo, if I'm not mistaken. Who, I think was his, well, I don't remember. Anyway, so basically, yeah, there are several things one can say, but maybe first I can. So we know that when you have a subgroup in a group, then the order of the subgroup has to divide the order of the group. That we had seen before. It's quite simple. And now the first Pseudo Theorem will be some kind of partial converse to that. So it's not true in general that if you have a divisor of the order of a finite group, then there will be a subgroup of that order. But if you write the order of the group as p to the m, where m is a prime number, times a number which is not divisible by p, then there will always be a subgroup of order p to the m. This will be called a p-pseudo subgroup. This is the first Pseudo Theorem, and then the other Pseudo Theorems say some more about what, how many there are and how they are related to each other.
Okay, hierarchy Pseudo. Hierarchy shadow. It's hierarchy shadow. Cool.
I cannot understand. Sorry. Anyway, so let's continue. So, so now let me state it. So definition. So a subgroup H. Can you please? I cannot understand. Sorry, I cannot understand. Can you please stop? So a subgroup H in G is called a p-pseudo subgroup. So now I got a bit confused. So anyway, let G be a finite group of order G equal to p to the m times R, where m is a positive integer and p does not divide R. So a subgroup of this group will be called a p-pseudo subgroup if it has the maximal possible power of p as elements. So if the order of H is equal to p to the m. So now the first Pseudo Theorem says says that G has a p-pseudo subgroup. It will be always such a group with this number of elements. So what I will do now is I will tell you all the three Pseudo Theorems, and I will draw some consequences, and then afterwards I will prove them, maybe partially in the next lecture. So this is the first result, and we want to give a corollary. The corollary is Cochise theorem. So this says the following. So if a prime p, a prime number p, divides the order of a group, then the group contains an element of order p, So then G contains an element of order p. It's also easy to see that in general, it's not true that for every divisor of the order of a group, there will be an element of that order. That's certainly not true. This, however, is very simple once one assumes the first pseudo theorem. So we take a p pseudo subgroup of G. So we take an element in H which is not the neutral element. So then this element must have some order. So we can look at the subgroup generated by it. It's a group. It's a subgroup of G. So its order must divide the order of the p pseudo subgroup. So it must be a power of p. So then the order of x divides. So maybe G has, say, p to the m for some m if the order of G is p to the m times r. So it is a power of p. And namely, it must be a positive power of p because x is not 1. So let the order of x equal to p to the r. Then if I just take x to the power p to the r minus 1, if I take, so this is obviously not 1, but if I take it to the power p, this will be precisely 1, so has order p. So as you see, it's kind of really trivial. One does the obvious. But the thing is, we do use that there is this p pseudo subgroup. So now we want to give also an application of the first pseudo theorem to do some classification of some groups. For this, I first do some kind of general lemma, some elementary fact, how one finds out that a group is a product of two subgroups, is isomorphic to the product of two subgroups. So we recall the product of groups. So if H and K are groups, then we had defined H times K was just the set theoretic product. And with the product, I mean with the group operation, H1 K1 times H2 K2 is H1 H2 K1 K2. Okay, so this is just the product of groups. This we had seen, this is always a group when we start with two groups. Now we want to see a criterion for a group being isomorphic to a product of two subgroups. Where is it? Yeah, I think. Okay, I'm not quite sure. Okay, so this is the following easy proposition. So let G be a group, and H and K normal subgroups. So assume the following. So first, we assume either that G can be written as G times H times K. That means as a set of all H times K with H in H and K in K. So every element in G can be written as a product of one element in H and one in K. Or, instead of this, we can also assume that G is finite and the order of G is equal to the order of H times the order of K. So this is the first thing we assume, one of these two. And the second one is that H and K don't intersect except in a trivial way. So the intersection consists only of the neutral element. Then G is isomorphic to H times K. Okay? So if you have two normal subgroups which have, for instance, the correct number of elements and intersect trivially, then G must be the product of these two normal subgroups. I mean, isomorphic to the product of them. Okay. So now, if it is like this, by definition, in such a product, every element of H will commute with every element of K. So let's first show that. Every H in H commutes with every K in K. So let's just write it down. So we want that HK is equal to H to KH for all H in H, K in K. So this is equivalent, by bringing it to the other side, that, say, H to the minus H to the minus 1, K to the minus 1, H, K is equal to 1. We just multiply by these elements. Hope this is right. Yeah. And now look at this. And now let's look at this. So for instance, if we look at this like this, we have H to the minus 1, K to the minus 1, H. By, this means it's a conjugation, it's K to the minus 1 conjugated by H to the minus 1. So this is an element in K. And this is also an element in K. So it follows that H to the minus 1, K to the minus 1, H, K is an element in K. And in the same way, if we look at it this way, we have an element in H, we conjugate it by K to the minus 1, and then we multiply an element in H. This is in H. And so this thing lies in this intersection of H and K, and so it must be 1. So this shows this fact that they commute. And now we can just define a homomorphism from the product to G. And we want to show it's an isomorphism. And the homomorphism is the obvious thing. We send a pair GH to the product of G and H in the group. So let theta from from H times K to G, so HK is sent to HK. So we want to claim it's an isomorphism. Let's first see, so show theta is an isomorphism. So first you have to see it's a homomorphism. So if I take theta of, say, H1 times K1, comma K1 times H2, comma K2. So here we apply theta to a product. This is, by definition, theta of H1, H2, K1, K2. This is H1, H2, K1, K2. But now every element of H commutes with every element of K. So this is equal to H1, K1, H2, K2, which is theta of H1, K1 times theta of H2, K2. Okay, so this is just the fact that every element of H and every element of K commute precisely gives us it's a homomorphism. And that it's injective is in some sense the same trick as before. So if H and K are in the kernel of theta, this means that HK is equal to 1. So that means that H is equal to K to the minus 1. But then H lies in H, therefore also K to the minus 1 lies in H, and therefore also K lies in H. So therefore K lies in H and it lies in K. So thus it follows that, say, H is an element in H intersected, large H intersected K, 1. And so it follows that HK is 1, 1. So therefore, the map, the homomorphism was injective. And surjective is basically what we asked here. We made the assumption here that either G is equal to H times K. So the product of all HK, which H and H, K and K. This assumption precisely says that the map is surjective. So first, so G equal to HK means theta is surjective. And the second assumption here, if G is finite and the number of elements in G is equal to the product, means we have an injective map from an element from a group with a certain number of elements from a set with a certain number of elements to another set with the same number of elements, so it must also be surjective. So if G is equal to HK, we have that theta is an injective map between two finite sets. with the same number of elements, so say of the same order. So it's bijective. Okay, so this was this simple fact. And now we want to use it. First, we give we prove something simple which has nothing to do with the Pseudo theorems. Just a nice little fact, which I think one could also prove in many other ways. Corollary. So if I have two relatively prime numbers, so let n and m be relatively prime, so the only common factor of n and m is 1, to some positive integers, then if I look at the cyclic group of so Zn times Cm is isomorphic to Znm. Okay. And this is a direct application of this proposition, which I can now prove. So we know that Znm is is abelian. So if I have a subgroup, it's a normal subgroup. So this thing with normal subgroup is automatically satisfied. So Znm has subgroups. So for instance, the subgroup generated by n with m elements and the one generated by m with n elements. And so this contains all multiples of n. This contains all multiples of m. As n and m, so the intersection of these two subgroups will be all numbers which are multiples both of n and m. But as n and m are relatively prime, these are precisely the multiples of n times m. And this means the element 0 in this group. So as n and m are relatively prime, we have that n intersected m is 0. No, the group is additive. So therefore, the assumptions are fulfilled, and it follows. So we apply the proposition. Okay. Now, so now we want. So we had seen before that so if p is a prime number, that all groups which have p squared elements are abelian. Now we want to give a complete classification of all groups with p squared elements. Namely, there are only two possibilities up to isomorphism. Either it is zp squared or zp times cp. And this is, for this we use the Pseudo theorems, but the first Pseudo theorem. So there should be a survey. So, corollary. I mean, we use the Cochise theorem. Corollary. Let p be prime. G, a group of order p squared, then G is isomorphic to zp squared, or G is isomorphic to zp times cp. You can easily see that zp squared and zp times cp are not isomorphic, because this contains an element of order p squared, and this one doesn't. in fact, the order of any element here is at most p. Okay. So by Cochise theorem, so now I want to prove it. So by Cochise theorem, our group contains an element of order p. What do you want to call it? Well, okay, A of order p. So we look at the corresponding subgroup, the cyclic subgroup generated by A. Now we take any element in G, we take some element in G which does not lie in H. And now there are, and we put H prime to be the subgroup generated by B. Now, as B does not lie in H, B is not the neutral element, so this cannot be the trivial subgroup. So it has to have at least P elements, so it can either have P elements or P squared elements. So thus, number of H prime is equal to P, or the number of elements in H prime is equal to P squared. So if this is the case, the group is, no, it means that H prime is equal to G and G is cyclic. So in the second case, H prime is equal to G and G is cyclic. And therefore isomorphic to the P squared. Now, if not, if H prime is equal to P, now we have two subgroups. Our group, we already know that every group of order P squared is abelian, so we have two normal subgroups, H and H prime. And H and H prime are normal subgroups. Of G. And, we have so if we take any element of so this group is cyclic, so any element of it which is not the neutral element will generate the group. So if the intersection of these two contains any element which is not the neutral element, then the intersection must be the whole of H or the whole of H prime. But we had assumed that, that our element B does not lie in H. So so therefore, it follows that H intersected by H prime just consists of the neutral element. No? If they contain something else, then H must contain the whole of H prime. And so we have the assumptions of our proposition fulfilled, so it follows by the proposition that G is isomorphic to H times H prime, which is isomorphic to ZP times ZP. No, because these are cyclic groups of order P. Okay, so this was this little fact. And now I want to introduce the second Pseudo Theorem. The second Pseudo Theorem says that all P pseudo subgroups of a group are conjugated to each other. It follows essentially from the definition that if you have a P pseudo subgroup and take a conjugated group, then it's also P pseudo subgroup because conjugation just sends a subgroup to another subgroup with the same number of elements. But the thing is also the converse holds. So let me show theorem. So second pseudo theorem. So the P pseudo subgroups. So I mean, one should maybe again say that the order of G is equal to P to the M times R, where R is relatively prime to P. So the P pseudo subgroups of G are conjugated to each other. So that means if H1 and H2 are P pseudo subgroups, then there exists an element G in the group G such that H2 can be written as G H1 G to the minus 1, which is as usual shorthand for set of all G H G to the minus 1 with G and G, with H and H 1. Okay, this is the second statement. I will directly go to the third pseudo theorem, which instead tells us to some extent how many P pseudo subgroups there are. I mean, it doesn't precisely tell us, but it gives us some kind of estimates about how many P pseudo subgroups there are. So this is the following theorem. So third pseudo subgroup, pseudo theorem. So again, we have the order of G is P to the M times R, where R is relatively prime to P. So maybe I still write it because so let G equal to P to the M R with P prime, and P does not divide R. Because here the numbers play a role. So let S be the number of P pseudo subgroups of G. So I cannot precisely say what this number is, but I can say two things. First, then S divides R. So it divides the rest here if I divide by the highest possible power of P. And S is congruent to 1 modulo P. So if I divide by P, S by P, I get the rest 1. So that means I can write S equal to AP plus 1 for some A in non-negative integer. Okay, so this is the third statement. So it gives us some estimate of how many P pseudo subgroups there are. So one thing how one can use these theorems very well together is one can, for instance, use them to show that our group G has to have a normal subgroup. Namely, if you can somehow use the third pseudo theorem to show that this number S is equal to 1, so that there's only one P pseudo subgroup, then automatically it has to be a normal subgroup. Because if you conjugate it, you get another P pseudo subgroup, and this always. But if there's only one P pseudo subgroup, it means that it must be the same as the group you started with. So maybe I write it down, because this is, a standard trick. Obviously, it's the simplest way. Life is not always so easy, but the simplest way how we can see that one can prove that our group has a normal subgroup is in this way. So this remark often can use this to show G has a normal subgroup. Namely, if the number, or just like this, the number of P pseudo subgroups can be shown to be 1, then the unique P pseudo subgroup has to be normal. Is a normal subgroup. Okay. Let me see. Okay, and now we want to give one more application of the pseudo theorems. You want to classify all groups whose order can be in a certain way written as a product of two prime numbers with an extra condition. Namely, these are just cyclic. So let G be a group of order P times Q, where P and Q are prime numbers. And we assume also, obviously we can, so these are different prime numbers, so such that P is, say, bigger than Q. Obviously, you can always assume that. But in addition, we want that Q and Q does not divide P minus 1. Then G is cyclic. That means G is isomorphic to Z PQ. Okay. So this is, quite often the case. So for many numbers of elements of the group, we know it's cyclic by this result. For instance, so e.g., if G is equal to 5 times 3, or 7 times 5, or 11 times 3. Anyway, there are many possibilities. So in many cases this applies, and in this case we already know it's cyclic, so it's a very simple group. So now we will, in some sense, we just in some sense put together what we had. So we will show that there is a unique P pseudo subgroup, a unique Q pseudo subgroup. These two, therefore, are normal subgroups, and therefore our group is isomorphic to their product. And this is a product of a cyclic group of order P and a cyclic group of order Q, and so it is cyclic itself. So that's how it goes. Let me do it. So let A and P be the number of P pseudo subgroups. Of G. Then it follows that NP is congruent to 1. So 1 mod p, and NP divides Q. But we have assumed that P is bigger than Q. So if it's congruent to 1 mod P, it cannot be bigger than P. So it must be that NP must be equal to 1. No, it's supposed to be divisor of Q, and there's there's no other possibility. And so now for NQ, so NQ be the number of Q pseudo subgroups. Of G. So again, we have NQ is congruent to 1 mod Q, and NQ divides P. So if NQ divides P, it must be either 1 or P. So if NQ is equal to P, then it follows that NQ is congruent, that P is congruent to 1 mod P. And mod Q, P is congruent 1 mod P. Then P is congruent to 1 mod P. Let me see. No, mod Q, obviously, mod Q. So that means so that Q divides P minus 1, because that's what it means. And so this, however, we had precisely excluded. This is in contradiction to our assumptions. So it follows that NQ is also equal to 1. So that means have a unique P pseudo subgroup and a unique Q pseudo subgroup, which are both normal subgroups. So let H be the unique P pseudo subgroup of G, and K the unique Q pseudo subgroup so then H and K are normal subgroups. Where is it? And we have that, so H has order Q, has order P, and K has order Q, which are two prime numbers, different prime numbers. So every element which is not 1 in H has order P. Every element in K which is not 1 has order Q. So they cannot have common elements except for the neutral element. So as H is cyclic of order P and K cyclic of order Q, we get that H intersected K must be only consisting of the neutral element, and the product of the numbers of elements is the order of the group. So it follows by the proposition that G is isomorphic to H times K, H is cyclic of order P, so this is isomorphic to ZP times ZQ, and this is isomorphic to ZP times Q. Okay, so this was this. So these were, for the moment, all the applications of the pseudo theorems I wanted to give. Maybe there will be some more in the exercises. So now we want to start proving the pseudo theorems. So this is somehow, I mean, it's not super difficult, but it's a little bit the most advanced part on in the group theory chapter, because we put a little bit together some of the things we have learned so far. In particular, we use in a slightly less obvious way what we have learned about group operations. So we want to use group actions to prove this. In particular, for instance, when we want to prove the first pseudo theorem, so when we want to prove the first pseudo theorem, we want to find a subgroup of order P to the M in G. And we want to do this by finding an action of our group G on something and an element such that the stabilizer of that element has order P to the M. So the stabilizer subgroup of G will be our pseudo subgroup. And for this, we have to find a nice action. And it turns out that the action we want to use is somehow comes from letting G act on itself, and then looking how it acts on the subsets of itself. And so I first want to briefly review how, about actions on subsets. So preparation on actions of G on subsets of G. So on the set of subsets of G. So first, let's just look. When G acts on a set S, it acts on the set of subsets of S. So let G act on a set S, then G acts on the set of subsets. So maybe I take here a finite set, I'm not interested in other sets, on the set of subsets of S. This is as follows. So we have S, and we have G acting on S. So let U in S be a subset. For an element G in G, we can let G act on it by saying G U is, or G times U. So if the action is G times U is the set, is defined to be the set of all G times U, where this is the action, with U in U. And it's straightforward to see this defines an action. If you have an action of G on S, then this defines an action on the subsets of S. So the map, so this defines an action of G on the subsets of S. Now, G, comma U now, that's straightforward to see. So furthermore, we know when we have an action, every element G, acts on every element G in G acts on S by bijections. So the map from S to S. So we know the map. So for all G in G, the map G times from S to S, which sends a small s to G times S, is a bijection, because the inverse is given by multiplying by G to the minus 1. So therefore, we can restrict the action here to the set of subsets with a fixed number of elements. We could look at the action on all subsets of S with 5 elements, or whatever. So thus, we get an action of G on the set of subsets of S with fixed number of elements. Okay. So this was okay. And one thing that we are interested in is the stabilizer of the set U under this action. So the stabilizer G U, by definition, it's the stabilizer for this action on sets. So this is therefore the set of all G in G, such that GU is equal to U. So we assume that our set S is finite anyway. So which is, we can also say this is the set of all G in G, such that G times U is an element of U for all U in U. No, because this says, GU is contained in U, but GU and U have the same number of elements, so therefore they must be equal. Okay, so this is the stabilizer for this action. So it's not that every element of U is sent to itself, but that U is sent into itself. Okay, this is the stabilizer. And now we want to look at this for two simple examples. Maybe I will only have time. Well, let's see. We will use this for the pseudo theorems for two actions of the group on itself. One is for the left translation, and the other one is for the conjugation. So let's look at the left translation. But I forgot one point, didn't I? Yeah, I first want to give some little result. So we want to know when is the stabilizer of a set U the whole of G. So when is U, so to speak, a fixed point of the action. So let G act on a finite set S, and let U be an S subset. Then the stabilizer of U in G is the whole of G, if and only if U is a union of orbits of G. Okay, that's almost trivial. Or it is trivial, but so one has to remember it. So GU is equal to G by definition if and only if G times U is in U for all U in U and for all G in G. That's what it means to be in the stabilizer. So if I take the set of all G times U with G in G, this is the orbit of U. So that's the same as saying that the orbit of U is contained in U for all U in U. And that just says, so the orbit of every element of U is contained in U, which is the same as saying that that large U is a union of orbits. Namely, precisely all the GU with U in U. Okay, so this was a simple proposition. And now we want to look at the action of G on itself by left translation and see what we can say in this case. So now we take that S be just our group G, so the group X on itself, and we want to look at the action of G on itself by left translation. So proposition let G act on itself by left translation. So GH maps to just the product, GH in the group. So let U be a subset.
Excuse me, sir.
Yes?
What is left translation? It's like we are moving a point. It's by.
Well, I had defined it in class. It's just the map which I wrote here. It's the map from G times G to G. G H is mapped to G times to GH. So just the action of G on itself is just by multiplying in the group.
Okay, sir. Thank you.
So let U be a subset of G. Then the order of the stabilizer of U will have to divide the order of U. Okay? And this, so the stabilizer always divides the order of U. We will use that fact for the proof of the first Pseudo Theorem. So in this case, we apply this theorem here, where we look at the action of the stabilizer on G. So let H equal to GU be the stabilizer of U, under the action by left translation here. So applying the previous proposition, proposition here. Now, obviously, the stabilizer of U acts trivially on U. So the stabilizer inside the stabilizer of U is the stabilizer. So therefore, it follows that, so applying through this proposition to H, we get that U is a union of H orbits, no? Under the left translation. Where am I? Go on. Okay. So it's a union of H orbits. H acts on G by left translation, and it's a union of H orbits. But remember that we had seen for the left translation, all the orbits have as many elements as the group by which we act, because it's just multiplication. There's always there's always the inverse. If an element in the group acts trivially, it must be the identity because it's multiplication in the group. So, but remember that for the left translation, all orbits have as many elements as the group which acts, so as have H elements. So therefore, U is a union of orbits. Each orbit has as many elements as H. So therefore, the number of elements of H must divide the number of elements of U. Divides. Okay, so this was the case, what we wanted to know about the left translation. And now we also will apply for some other of the pseudo theorems, we will apply the conjugation action, in particular for proving the third pseudo theorem. And so for that, we want to see, to say something about the action by conjugation on subsets or subgroups, on actually in this case the subgroups of G. So definition, oops, what shock is that? This one is better. So not all chalk is equal. So let G be. Let. It's also not good. H is subgroup. So for G in G, we have the conjugate subgroup. It already is just G H G to the minus 1 with it's the set of all G H G to the minus 1 with H and H. We can easily see that this is a subgroup. So this is a subgroup of G. And so in this way, and obviously sending the map G, comma H to G, H, G to the minus 1 is an operation of G on the set of subgroups of G. Action G on the set of subgroups. This one is good. Okay, so we want to see a couple of things about this, and then I will stop. And we have finished the preparations. So what is the stabilizer? Stabilizer of a subgroup H is what? Is an H, which is the set of all G in G, obviously such that G, H, G to the minus 1 is equal to H. And this is also called the normalizer of H. We should write it better. Lie of H in G. Now you can see, it's easy to see that this normalizer is itself a subgroup of G. I mean, that follows essentially like from definition. And by definition, H is a normal subgroup of this NH. So we can use this to make the following simple remark. So in particular, remark. So as this is a subgroup, and H is a subgroup of NH, and then H is a subgroup of G, we get that the number of elements in H divides the number of elements in NH, so the order of NH, and this divides the order of G. So this is the first remark we want to use. And the second statement is, if we put C to be the number, so the number of different conjugate subgroups of H. So by which I mean, so these are subgroups of G which are conjugate to H, and how many different ones are there? Then we have that by the orbit stabilizer theorem, we get that the number of elements in G is equal to the order of the normalizer of H times this number C. Because this is just, if we look at the conjugation action, the number of different subgroups conjugated to H is just the number of elements in the orbit of H under the conjugation action, and NH is precisely the stabilizer of H under the conjugation action, and so the orbit stabilizer theorem says precisely this. And this statement we will use. We will use the conjugation action and this statement to prove the third Pseudo theorem. Okay, so this is maybe all I wanted to say for now. Now I've done the preparations. Now the one starts with the actual proof. Okay, but maybe my time is up and I can do it the next time. Okay, thank you very much. Are there further questions? Okay, doesn't seem to be the case. Maybe I was a bit. Okay. So then, thank you very much again. I'm not yet quite sure when we will see each other again. We are scheduled for next Wednesday, but most likely it will not be possible next Wednesday, and maybe not even next Friday, because there's the scientific council, and I'm supposed to be at the scientific council at the time of our lecture. And so, and I have some other meetings with members of the scientific council also at other times, so it's not clear whether there's any time next week when I can see you. But anyway, I'll try to figure out. Okay. So enjoy your free day, the weekend and the free day afterwards. But as I said in the beginning, don't enjoy it too much. I mean, in the sense that you are careful. Okay. Have a nice weekend.